This bar chart compares energy consumption per capita across the globe. India currently sits near the bottom of this list, with the average citizen using just a fraction of the power consumed in the United States or Europe. But that historical baseline is shifting. As India industrializes at a national scale, millions of people are moving toward energy-intensive lifestyles for the first time. This growth isn't just about domestic use. It's being driven by massive new facilities, AI data centers, specialized giga-factories, and green hydrogen plants. These industries operate on a scale that dwarfs traditional manufacturing. A single data center or chemical hub requires a constant high-voltage stream of power to keep its processors and reactors running. This creates a difficult requirement. India must feed an exponential economic boom while hitting a zero-carbon footprint, an objective that is physically impossible using the grid's current structure. Generating clean power is the starting point, but the real obstacle to industrial growth is the timing of that generation. Engineers call this the 24/7 challenge. It is the requirement for a grid to provide an uninterrupted, round-the-clock supply of electricity, regardless of weather or the time of day. Modern infrastructure, like an automated gigafactory, cannot pause for a passing cloud or wait for the wind to pick up. Even a micro-fluctuation in voltage can cause millions in damage and operational delays. This graph illustrates the problem. This flat horizontal line is the constant energy demand of a data center. These erratic, peaking curves show the actual supply from solar and wind. They rarely match. To sustain industrialization, India cannot rely on simple generation alone. It must build an interlocking grid that synchronizes these sources into a 24-hour supply. During the day, solar farms often produce more electricity than the local area can use, yet industries face a power deficit the moment the sun sets. One way to manage this is through pumped hydro. This cross-section shows the three components: a lower reservoir, a turbine channel, and a higher elevation reservoir. When solar production is at its peak during the day, that excess electricity is used to pump water up to the higher reservoir, effectively storing the energy for later. When demand spikes at night, the water is released. It flows back down through the turbines to generate clean electricity, precisely when the solar panels go dark. By combining wind and solar with this kind of mechanical storage, the grid can provide a stable, predictable baseline of electricity for heavy industry. However, even a perfectly stable grid only provides electricity. Heavy industries like chemical manufacturing require more than just power. They need raw carbon molecules to create physical products. In sectors like fertilizers and high-performance plastics, electricity cannot replace the molecular feedstocks needed for production. To secure these materials, India is launching new coal gasification projects. These plants turn coal into the gases needed to synthesize vital industrial chemicals. The conflict here is clear. Using coal to create chemicals releases significant CO2, which threatens the very zero-carbon goals the country is trying to reach. This is where carbon capture and conversion becomes a necessary addition to the industrial process. This diagram shows the process in action. Instead of letting CO2 escape into the atmosphere, the exhaust from the gasification plant is diverted and isolated into a capture unit. Once isolated, that carbon is chemically converted. Instead of a waste product, it becomes a raw material used to produce green hydrogen and other high-value industrial chemicals. Creating this kind of closed-loop system requires specific, localized engineering rather than off-the-shelf global solutions. Biogenic Urja is currently developing their own patents and IP for this exact transition, focusing on new technologies for carbon conversion and the production of green hydrogen. By integrating these capture and conversion technologies directly into the plant, India can turn an emissions liability into a self-sustaining source of green chemicals. When we look at the entire national infrastructure, these separate technologies start to function as a single synchronized machine. Solar generation provides the daytime surge, pumped hydro bridges the nighttime gap, and carbon conversion handles the molecular needs of heavy industry. This integration allows India to sustain its rising per capita energy consumption while actively decoupling that growth from its carbon footprint. If a nation of over 1 billion people can industrialize while neutralizing emissions, it offers a functional alternative to historical reliance on fossil-fueled expansion. By building this interlocking green grid, India is demonstrating how a high-growth economy can stabilize its own industrial future while contributing to a zero-carbon world.